Welcome back to Chapter 4, Effects of Electric Current, and today we're going to study short circuit. I'm sure you might have heard about buildings catching fire due to short circuit. So let's understand what is the short circuit. Normally in our plugs that we have at home, we normally have three wires, whether it be at the meter point or whether it be at any plug point. There are three wires. One is live, one is neutral, and one is the earthing. Okay, the live and the neutral are insulated copper wires. There is a coating of insulated material, but sometimes either due to the fault in the equipment or because of too much of current passing through it, the insulated material on the live and the neutral wire melts, and as a result they come in contact with each other. And the moment they come in contact with each other, tremendous or huge amount of current flows through it, producing large amount of heat. We have already studied about the heating effect of electric current. So large amount of heat is generated, and if there are inflammable material like plastic or these wires, this plastic material, all these, they normally catch fire. And if this catches fire, if there is wood or cloth or anything else around, that also starts catching fire. So what is the best way, the best solution to avoid any further mishap? Of course, putting off the mains. But many times we may not be at home, or we may not know where the main switch is, or we may not even we may not have the time to put off the main switch. In such cases, there is a solution made already in these gadgets. The meter itself has something that is called as a fuse wire. So let's understand the role of fuse wire. Now, a fuse wire is a precautionary measure. Now, what is done? You can look at this fuse wire here. Okay, so as a precautionary measure, we have the fuse wire at the main supply, where the main supply is. Okay, so at the main switch, we will have these type of fuse wires. These wires are very, very thin, normally made up of material with very low melting point like tin, lead or zinc. And the moment there is a tremendous current flowing, like in case of short circuit, okay, when too much of current is being pulled in the house, then the meter, the fuse wire which is placed at the meter gets blown off. The moment this gets blown off means burnt off. It starts melting, and the moment it melts, it breaks the circuit. As a result, the current that was entering our homes now, okay, will not enter anymore, and at least further entry of current will stop. Okay, will the fire go off? Fire may not go off immediately if it's already a huge fire. But if it's just the starting of it, then probably this can be controlled by this method. Okay, where the fuse wire is blown off, that is, it melts on its own, breaking the circuit, and no more electric current comes into our homes. So this is one way of avoiding any type of mishap. You have different types. These are in the porcelain container, but nowadays you also get these type of fuse wires. Okay, now there is something also called as overloading. The fuse wire is also needed not just during short circuits but also during overloading. Now, what is overloading? During summer especially, many people use variety of gadgets. We use AC, which requires huge amount of electric current. Then there are various other fans are on, electric lights are on, and it's not just in our homes, it's in multiple houses. So simultaneously, a large amount of current is used by many people. And as a result, the capacity of the transformer which is supplying us electricity goes low. The transformer cannot supply that much of electric current, and all of a sudden there is a total blackout. Okay, that is, the fuse wire blows off and there is no more electric current entering into our homes. This is called, or this is due to the overloading that the fuse wire has blown off. So the fuse wires can play its role in two major issues. One is for avoiding any type of mishap due to short circuit, and secondly due any type of overloading that might happen in our homes. Okay, now you may not see the earlier type of the circuit breakers, that is the fuse wires that we have seen. Nowadays, many gadgets like our inverters and all come with these type of MCBs, colorful MCBs. Okay, now what are these MCBs? They're called as miniature circuit breakers. So they break only a small circuit for that particular gadget, like for our inverter. Okay, when there is overloading, like you're not supposed to use very heavy load equipments on our inverters, okay, because the battery will go flat immediately. So therefore, when there is overloading, then these miniature switches they will fall down. Normally if they are up, they will come down. Okay, that shows that the circuit is broken. The switch is open now and the circuit is broken, and therefore that particular gadget will be saved from overloading or from getting spoiled. Okay, the gadgets can get spoiled due to too much of electric current, and therefore small miniature circuit breakers are used in many gadgets nowadays, and they look something like this. Okay, these switches. Now we come to another simple topic, that is simple electromagnets. I'm sure in 8th standard you have made these type of simple electromagnet, and you have also conducted this experiment. All you need is a cell or a battery, okay, 2 cells or 2 battery, whatever. Then you need to have a conducting wire. This one end of it is attached to positive pole. It is wound around a small matchbox, and in the matchbox we just placed a magnetic needle, okay, and taken many turns, and the other end of course to a switch if necessary, and then attached to the negative pole. Now when the switch is open and no current is flowing, then there is nothing is seen, there is no movement in this magnetic needle at all. That means there is no deflection, so there is nothing. Okay, when will the needle deflect? Only when there is magnetic field. Like if you bring a bar magnet close to this, then it will definitely start deflecting. But we notice that when we complete the circuit, electric current is flowing through this, and this magnet starts, the needle starts moving, starts deflecting, showing that there is some current, there is some magnetic field that is generated. Where did the magnetic field come from? We have not used any magnet in the circuit. This has come from this conducting wire, which now acts as a magnet when electric current passes through it. And this principle has been used in this simple electromagnet, which I'm sure you might have done in 8th standard. All you need is an insulated copper wire. Then you need a nail, okay, or a needle, a big needle, and a battery. Now what you do is wind this copper wire multiple times on this iron rod or on this nail and attach it to a cell. The moment the circuit is completed, bring some pins close to it, and you will see the pins get attracted, telling you that this little nail is acting as a simple electromagnet. That means this nail has generated magnetism. Okay, from where did the magnetism come? Of course, from the electric current. That means when electric current passes through a conductor, it behaves like a magnet. Okay, and it was this magnetic effect of electric current, or called as electromagnetism, was discovered by scientist Hans Christian Ørsted in 1820. And he noticed that whenever electric current passes through a metal wire or a conductor, magnetic needle placed close by will get deflected, showing that the wire is acting like a magnet now. He thus pointed out the relation between electric current and magnetism. Hence, the unit of the intensity of the magnetic field that is generated in the wire is normally called as Ørsted. Okay, after the scientist Hans Christian Ørsted. Now, suppose if the conductor is placed vertically, if this is the direction of the conductor, then where are the magnetic fields generated? So this is a simple experiment that you can see here. Iron filings is placed. If the conductor is allowed to pass through and through this cardboard, and if we throw some iron filings, they arrange themselves in concentric circles. The circles are very, very close when it's close to the conductor, and then they go wider and wider, further and further when they go away from conductor. That means maximum magnetic effect is found very close to the conductor, and as you go away from conductor, the magnetic effect becomes lesser and lesser. Okay, so normally the magnetic field is generated around the conductor. Fine. So now let us understand what is this. Before that I will explain to you something else. What will happen if a magnet rotates in this way? Okay, let us see here. If you bring a magnet in close contact with this circuit, then what happens? Now in this circuit, if you see, there is no battery, no cell, nothing except a galvanometer. A galvanometer detects, traces even slightest amount of electric current flowing. So when the magnet moves in presence of the conductor, this galvanometer moves, showing that electric current is generated. Okay, so here you find electric current being generated in this coil because of the presence of the magnet. Okay, so this, what is this called now? This is called as induced current, because here we are creating current. In the previous case, we created magnetic field by passing electric current. In this case, we are not passing any electric current, but we are passing a magnet. We are moving a magnet in and out, okay, in presence of this conducting wire, and this conducting wire is now generating electric current. Therefore, this current generated is called as induced current. If you remember, you studied this in the 8th standard also, electromagnetic induction. That is induced. The current is induced in this coil due to the presence of the movement of the magnet. Okay, now let us understand what is this right hand thumb rule and what is this meant for. Now when a conductor, as I showed you in the previous case, when the conductor is placed vertically, the concentric circles shows you the direction of the magnetic field. So right hand thumb rule is used to find out the direction of the magnetic field. In which direction is magnetic field generated? This experiment is also called as Maxwell's corkscrew rule. Now Maxwell's corkscrew rule is similar to the right hand thumb rule. What does it say? Now if you hold a conductor in your right hand, okay, now my right hand might look like a left hand here. Okay, so if you're using if you're holding a conductor, okay, with your right hand, and the thumb is pointing towards the the thumb is pointing along the direction of the current. Now look in which direction are the your fingers curling. The thumb is giving you a direction of electric current, which is vertically. Okay, and look at the curl of your fingers. Now if you're holding it like this, it's curling. Is it curling in clockwise or anti-clockwise direction? Yes, it is anti-clockwise direction. So these concentric circles or the magnetic field is generated in anti-clockwise direction. That is what we learn through the right hand thumb rule. For right hand thumb rule, you need to hold the conductor in such a way that the thumb is pointing in the direction of the electric current, and your fingers, look at the curl of the finger. Okay, the curl of the finger is in anti-clockwise direction. That shows you the direction of the magnetic field. So basically the right hand thumb rule is meant for showing you the direction of magnetic field. Okay, so in the next video we will study more about solenoid. Till then, keep studying. Bye bye. God bless.